Okay, so thanks everyone for tuning in. Today we have Chris Akers, who's going to tell us about evaporating black holes and I don't know, all sorts of interesting stuff. So Chris, thank you very much and take it away.
Thank you, and thank you for the invite. I'm excited to talk to y'all about this. So the main point of what I'm gonna discuss is a particular simple model of black hole evaporation. So I'm gonna spend some of the time giving background that will motivate the model. Then I'll describe the very simple model, and then I'll talk about what we can learn from it. Okay, so first with the background. So let me switch the cameras. Great, and yes, please tell me if this is illegible. So still talking about background. Let me describe the familiar Hawking story in a way that will be conducive to the later discussion. So in Hawking's story, there's, say, a black hole that forms from collapse. So this is a collapsing shell of matter. And we'll put ourselves in asymptotically ADS. And let me not worry too much about what happens in this top right corner. Maybe black hole is small and it evaporates, and so we need to return to something asymptotically ADS, or maybe it's large, but we'll ignore that subtlety for now. Okay. So given this structure, there's a horizon here, and of course, this extends infinitely to the past. And the important part of Hawking's calculation for us is that there is a growing entanglement between the inside and the outside, because there are partner modes, say one on the inside here, and then one on the outside here, that are entangled. This blue line is just supposed to represent some entanglement. I don't know if you can actually see that it's blue versus black.
No, the color shows up fine on our screen at least.
Okay, great. Okay. So this ultimately, so if the black hole is small and evaporates here, then this ultimately leads to a paradox. The paradox is that because Hawking effectively assumed a state of the radiation that, I'm going to be sort of schematic here, where you're summing over all frequencies and excitation numbers. The inside and the outside are, so this is the inside radiation factor, and this is the outside radiation factor. And then there's some like Boltzmann weighting. So this is roughly the state that he dealt with. Taking this state, if you trace out, say, the inside, just to see what the state of the outside is, you get a reduced density matrix that is thermal. And this leads to an issue because when a black hole, say, is over halfway done evaporating, the von Neumann entropy of the radiation is bigger, or towards the end of evaporation is much, much bigger than the area of the remaining black hole divided by 4G. And this is a paradox because we like to think of A over 4G as the log of the number of states of the black hole. Maybe you could quibble with that, but that seems like it's on solid ground. And so there's this bipartite entangled state between the radiation on the outside and the black hole, which is sort of oversaturating what the black hole can do, what it can entangle with. Right, so the black hole is supposed to be responsible for more entanglement than it has microstates available. So this is one way of discussing the black hole information paradox. And as, again, all of you know, I'm sure, there are these updates that propose to resolve this with the island formula. So here's quick review of islands. I should say this discussion is important for later on, because a lot of what this simple model is supposed to do is explain some confusing aspects of the island formula. So that's where we're going. I just want to lay out the island formula, point out what at least I found sort of confusing about it. And then when I tell you the simple model, we can talk about what the simple model is teaching you about it. So the familiar setup of the island formula is that say this one, where you have a two-sided black hole. So now it's asymptotically ADS, and this is an asymptotic boundary, and this is also a separate asymptotic boundary. And in these papers, they have coupled each asymptotic boundary to its own non-gravitational flat space. Okay, and so so the region inside the original square is gravitational, and then gravity sort of turns off exactly at the asymptotic boundary, and it becomes flat. And there are sort of two versions of this. The easier to comprehend one, the easier one mathematically, is the one where you consider a system coupled like this at all time, and you prepare the state at t equals 0. That's sort of in the Hartle-Hawking state of this entire space-time. Just to connect to this original story about evaporation and also the model that I'm going to present, I'm actually going to talk about the more complicated setup that was originally in the paper by AEMM. So let me actually put down some citations here. So when I'm talking about islands, these are some of the papers that I'm thinking about. And I'm specifically going to talk about the setup that was in this second one here by Almeri, Engelhardt, Meroff, and Maxfield. So in this setup, it's a little bit modified from that because it'll be two-sided. They do discuss this though. In this setup, instead of being coupled for all times, they sort of turn on the coupling at a certain time. So we'll say t equals 0. And so even though I've drawn it like it's coupled to the past, that's just for convenience. And really you should understand that the coupling between the gravitational side and the gravitational side and the non-gravitational sides is happening at this dot. It's starting at this dot and then it's persisting for all time. Okay, and so what this coupling does is it allows the black hole to evaporate because the radiation that's in the bulk, the gravitational bulk, is allowed to escape. And unlike the eternal case, which you may or may not be more familiar with, we did not prepare the flat space region in a state that has radiation flowing into the gravitational region. So there's radiation leaving the gravitational region, but none coming back in. And that's happening on both sides. I'm doing that for simplicity. Okay, so the coupling is happening like here and here. And what you're supposed to imagine is that there's, say, Hawking modes. There's Hawking modes, say, here that free stream out through the boundary, and ditto here. They sort of stream out. Okay, and then each of these had partners on the inside. Let me draw them in blue so I can refer to the just simpler. So the blue guys are the interior. And this blue guy is supposed to be entangled with this black guy, and this blue guy is supposed to be entangled with this black guy. That's the semi-classical entanglement structure, at least. Okay. So in this setup, again, we have a similar issue to the one that we discussed in the Hawking context up here. Because what happens, at least naively, is that, say we're interested in computing the entropy of certain regions in the non-gravitational region. So a very simple region we could consider is, say, a region that's like the union of that and the union of this. And I've added brackets here just to denote that's where I'm ending. So it's the region sort of outside of these brackets that I'm computing the entropy of. They're sort of far away from the boundary, but I did that just for drawing clarity. I'm imagining that they're in fact most of the flat space regions. Okay, so if this is the region I define, I could consider how the entropy of this region changes with time, where each later time sort of moves this up. So say a later time would be, well, it's getting cramped in this corner, but let me draw it like this. the later time would be the union of this and this, for example. So I've just moved both up in this diagram. And what you can convince yourself of is that as I move these regions up, so let me just call these regions R. So this is R, well, the union of them is R. And R we can say is a function of t. So this is R at t equals 0, and this is R at some later time. And then I can ask about the entropy of R as a function of time. And we're supposed to understand that it, I don't know if it starts at 0. It starts somewhere small, not 0, and grows. So it's sort of growing linearly. And this is the curve you expect. Eventually, it'll plateau way later because the black hole is fully evaporated. So it's growing linearly. And the reason you're supposed to expect this curve is that these exterior Hawking partners leave, and then they exist on the region R at late times. And because this guy is on R for late enough times, that adds to the entropy of R because he's entangled with this blue guy. Okay, so at later times, the entropy of R increases. And it sort of does that until the black hole is done evaporating. So this is a problem because, say at late time, so say this is the page time. So this is when the entropy of, so this is the line that says the entropy of the radiation is now equal to the area of the remaining black hole. I've drawn it here in a way that's indicative of the fact that that's much before the entropy stops growing linearly. So in all of this region, while the black hole is evaporating, just like before, it will come to a point where the area of the black hole is much smaller than the entropy of the radiation that it's supposed to be entangled with. And that's a problem with that's this problem, the problem with this that we ran into before. Okay, so all I've done is just draw this new setup and this old familiar problem in this setup that y'all are probably familiar with this problem in this setup. Okay, so what we're told is that the island formula comes to the rescue, and then the island formula is actually, it's a really nice resolution, and what it says is the following thing. So let me write it and then explain it. So it says that the true way that you should compute the entropy of R is not the naive way that we discussed here that would lead to linear growth for a long time. The true way that you should compute the entropy of R is to first consider a bunch of regions I. So I could be a region like this. So it has to be a region in the gravitational region. Right, so this is, so I apologize for this diagram getting cluttered, but this could be a candidate I. I've drawn it here, and this is actually what the real I is going to look like. But it could, in principle, look much crazier. Like it could be, you could consider I as they're outside the horizon, or just any general region on in the gravitational part of this diagram. So you're supposed to consider all such I, and you consider this quantity. You consider the area of the boundary of that I over 4G plus the entropy of R union I. And what you want to do, so that's, you consider the entropy of the fields that we just discussed in this diagram that live on R, but not the entropy on R, but the entropy on R union I. So that this union of these three regions, that's the entropy that goes here. And then you consider this quantity, and then you extremize with respect to I. So you have to make sure that this quantity is extremal for the I that you find. And then you take the minimum. You take the minimum, you take the I that minimizes this. Okay, so so let me quickly mention one thing that I'm going to come back to a lot over the point of this, over this discussion. And that's, this formula, at least at first, is a little bit confusing because on this side, we're trying to compute the entropy of R. But here, the entropy of R is in some sense showing up. So it's sort of self-referential, seemingly. But in fact, it's not. The R that goes here is actually some sort of semi-classical state. So it is not the entropy of the state you believe the radiation to actually be in. So maybe the state is actually in some complicated state with low entropy. What goes here is the state that Hawking computed, like this, the sort of thermal radiation out state that we believe is entangled with degrees of freedom in I. So I'm going to come back to that a lot, but this is the basic prescription, and as you know, the reason why this saves the day is that it will stop the entropy of R from growing forever. So the entropy of R seems to grow for a long time, well past the time where it should have stopped, because we were effectively using only the trivial I. We were effectively not including any I in the bulk that wasn't empty. In fact, there's another I that becomes dominant sort of at this time, and that I looks like this. So in this setup, it's an island. So I say I is for island. It's an island that sort of takes up the entire interior, and at later times, the island also sort of pushes to the future and stretches out such that it's always somewhat close to the horizon. And what happens is that if you consider the entropy given that I, it would look something like this. It would start, that I starts large and then decreases to 0. Or yeah, maybe I shouldn't go all the way to 0, but it decreases and sort of back to the same point. So forget this part. Okay. So why does it do that? It does that because all these modes that are exiting the gravitational bulk and at late times sitting in the region R are entangled with these blue modes that are supposed to lie in the region I. And so this part of the entropy of R formula does not increase with time because all these extra modes that enter R aren't adding to the entanglement of R union I. Their purification is an I. It goes down because this term goes down. So this term sort of isn't changing with time appreciably, and this term starts large because it's basically the area of the black hole, and then it decreases to some very small value, where this part decreases to 0 because eventually the black hole evaporates. So what this tells us, because of this minimization requirement, is that we should be keeping track of the entropy according to all i's that are extremal. And so it's non-trivial that this one is extremal, but it is. And the leading piece, the trivial I corresponds to this line. This non-trivial I here corresponds to this line, and the actual entropy of R tracks the bottom. So it goes up to this point, and then it goes down. So it tracks the minimum. And then this is the so-called page curve that we wanted, which is great. So what the island formula gave us is a prescription for computing the page curve.
Chris, can I ask about your formula there that you wrote down?
Yes.
So naively, I would have looked at this as sort of like this, the usual generalized entropy formula in ADS CFT, where on the right, your S of R is the boundary entropy, and on the left, the S is the boundary entropy, and on the right, you have sort of the leading order area term from Ryu-Takayanagi, and then the entropy of all the bulk fields, which I guess is sort of semi-classical.
Yes.
Can I still think of this in this way? The reason I'm confused is because then your semi-classical bulk fields are in this other flat space region you glued on. So does that mean that that is somehow also dual to your new, like your boundary CFT also now contains a description for that new region?
The short answer is I basically agree with everything you just said, and that's going to be almost the point that I'm building up to. However, I would say that you shouldn't understand the modes here as being encoded in the boundary CFT, but the relationship is what you said. So this is basically this Ryu-Takayanagi plus FLM formula.
So the entity on the left is still is the boundary entropy in the CFT.
So yes and no. If you mean by that it's actually the entropy of like in some actual CFT that lives somewhere, then I would not agree. But if what you mean by that is that you should consider this as sort of the entropy of the full algebra, and this is the entropy of some logical subalgebra, then I completely agree. And in fact, that's what I was just about to start talking about.
Okay, and I'll see where you go then. Thanks.
Okay, yeah. Great. So there are, so just exactly like Ro anticipated, there are sort of two questions that are that were a little confusing to me personally about this formula that I want to clear up with this simple model that I will describe to you. So the first question is, what is the relationship between R on the left-hand side and R on the right-hand side? So we're told that on the right-hand side, it's like the semi-classical state on R, but why is that the state that has to be plugged in to compute the correct entropy of R on the left-hand side? Why is it the semi-classical state? And like, what's the relationship between those two specific states? And I'll just jump ahead. So the answer is going to be one of quantum error correction. That's what I'm going to argue to you as the answer. So you should understand R on the left-hand side as the physical algebra. Like, it's associated to the physical algebra. So just like if you're used to thinking about ADS-CFT as a quantum error correcting code, we talk about the CFT as being the state according to the full algebra, and then the bulk state as being some sort of logical subalgebra. And I'm going to talk about that.
By algebra, do you just mean with the set of all like low-lying primary states, or what in the CFT?
Yeah, I do. I mean like the full set of operators versus some restricted set of operators. That's right.
Okay, thanks.
Yeah, and then so R on the right-hand side will be some sort of logical or code subalgebra. And explaining what I mean by this will be the point of the last part of the discussion of this talk. And there's so this is the main thing I would say that I want to answer, but there's a smaller thing that this model is also supposed to address. So that smaller thing is, in all of these discussions, so the island formula seems to rely heavily on quantum extremal surfaces, and it's not clear, you might wonder how irreplaceable are the unique aspects of quantum extremal surfaces. Could I have, like, are they truly different from RT, and that RT would never, regular Ryu-Takayanagi could never have had something like the island formula? That's the question. And the answer I'm going to claim is that, in fact, you can find a model that has these features with RT. That's going to be sort of the point, the motivation for this model. And these are connected because, so this was historically the original goal for writing down this model, just so that we could personally understand it, this aspect. But this connects to this top question, because once you do write it down in terms of a model that has the same island formula in terms of Ryu-Takayanagi, instead of ever having to deal with quantum extremal surfaces, it became clearer to us the connection to quantum error correction and how you should think about all the terms in the island formula. So these two questions are ultimately related, and that's what the model is supposed to address. Okay. So now I'm going to turn to actually describing the model. Great. Okay, so as I said, the point is to find a simple case where the island formula pops up. And hopefully having such a familiar setup with the island formula will give us intuition about what it means. So basically what this model is going to be, we just imagine that instead of a black hole radiating Hawking photons, we have a large black hole radiating smaller black holes. So in fact, what it's going to be, this model of black hole evaporation is really a sequence of multi-boundary wormhole states. And there's pros and cons to this model. I'm sort of telling you a lot about the model before I actually tell it to you, but telling it to you will be short. So the cons are, of course, that the dynamics are unphysical. We don't actually expect a large black hole to radiate into smaller black holes. But I'm going to argue that this is okay because the questions we want to answer about, say, the island formula are questions sort of at the level of the state, about the structure of the state, and don't depend so strongly on exactly the dynamics used to get there. So this will be a sort of different sequence of states, but they're going to have similar structure. They're still going to have the island formula, and that's supposed to extract the important features of the island formula. And here are the pros. So we're still going to get the page curve. We're going to use only regular classical RT surfaces, not quantum extremal surfaces, in our black hole evaporation model. It's going to very nicely match ER equals EPR intuition. And this was the thing that really sold it for me, is that it makes the connection with quantum error correction intuitive, or at least more intuitive. Okay. So you can come back to this list after we see the model. So here it is. So I'm going to draw two sets of pictures to try and explain it. But really, as I said, you should imagine it's just one big black hole radiating smaller black holes of a fixed size. So it's a sequence of states. State one is this. So here is, spatial slice of a 1 + 1 dimensional CFT. This is like our holographic CFT. And it's dual to some large black hole. So this is the bulk now. So this shaded region is a large black hole. So I'm going to refer to this CFT, or equivalently its bulk state, as the black hole. So this black hole actually plays the role of the black hole in our model. There will be other black holes that play the role of radiation, and it's important that this is very large. I don't know why I put quotes. It's just large. Okay, and then state 2 has it radiating one black hole, and say state 3 again has the same. So it's the same CFT, and then now I have to imagine that there are more CFTs. These are these CFTs are disconnected. They don't. They're entirely different spheres. This is still the black hole CFT, and it has its dual is still a large black hole, but this black hole is now slightly smaller than this guy. That matches your intuition that a black hole, when it radiates, gets slightly smaller. And these guys are dual to, say, ADS-sized black holes. So these black holes, these bulks that I've drawn just have a black hole in the middle that is ADS-sized. And both of these CFTs,
sorry, a question, shall we think about these additional boundaries as being there from the start?
Yes, that's a great point. Yeah, so you should think about them as being over here, and there's actually going to be a lot of them. I just didn't draw them.
Okay, thanks.
Yeah, great question. Glad you asked it. Okay, so these are the radiation CFTs, or equivalently the radiation bulks. Okay, and so what's the state of the union of these? Well, the state of the CFTs I'm preparing in some entangled states that we actually know a lot about. So I could prepare this entangled state of these CFTs. So the goal was to prepare a bulk state that is like a multi-boundary wormhole. And we know how to prepare both that bulk state and the boundary state using path integrals. So the boundary state I can make by doing path integrals on quotients of a Poincare disk. This is the Schottky construction, for those of you who are familiar with that. And then the dual bulk state basically fills in that geometry, and this is the handle body construction. Okay, so this is some entangled state between these three guys, and I can actually draw maybe a more illuminating picture where, say, this circle, so this is a picture of the same state that may be more illuminating because it'll draw the bulk connectivity explicitly. So this is the black hole CFT. This is, say, this radiation CFT.
One question.
Yeah.
Are these, so these black holes, the black holes are supposed to be connected via some interior?
That's right.
Okay.
And you will see that with this picture I'm drawing.
Okay, thanks.
So both of these are the radiation. And the way you should imagine the interior is like this. So it's like some pair of pants. And the horizons are as follows. So in blue, I'll draw the horizons. So this big horizon is, closer to this black hole CFT. And I'll draw it in a blue dotted line. And it goes around the back, of course. And then say this guy's horizon is here. And then this guy's horizon is here. And so in between all these blue dotted lines is this shared interior. And you can see where I'm going with this by noting that if we compute the entropy of these radiation CFTs, whether or not the RT surface goes up to just these guys or this guy depends on which is more minimal. So early on in the radiation process, there aren't many of these radiation CFTs. And so these guys will be far more minimal than this guy. And so the entropy of the radiation CFTs, the RT surface will only go up to here and not here. But late in the radiation process, we'll see that it goes all the way up here. So they gain the shared interior, and the shared interior will therefore have the interpretation of the island. That's looking ahead. So let me just finish up by saying what state M looks like. So let's just say state N, say little n. Okay, so let me put a wall here to denote, right, this column is state 1, this is state 3, and this is state N. So my circles are getting worse and worse. So this again is the black hole CFT. The black hole now at state N maybe is very small. Not very small, still bigger than these ADS size guys, but much smaller than it started with. And then now there's N minus 1 of these ADS size guys. And that's little n minus 1 of these guys. Okay, and as you might imagine, so again, we know how to construct this entangled state that's dual to this connected wormhole geometry. So this is a state that we understand very well. That's part of the what's so great about this model, is that these are states that we understand. And so here I put some dots to denote that there might be a lot of boundaries in there. And so there's n minus 1 of these radiation guys. And again, the horizon of the big guy is here, but now he's not so big. And then the union of all the horizons is this lower blue line. The union of all the horizons of the ADS size guys is the lower blue line. Okay. So,
sorry, a question here. Can you be a bit more specific about RT surfaces that you would be considering? I mean, like for what bipartition of the boundary Hilbert spaces?
Good, thank you. So I'll actually I'll give you a short answer now and a longer answer in about 3 minutes. So what I want to consider is the entropy of all of the radiation guys. So the union of all of these boundaries, excluding this guy. So the union of these excluding this guy is mostly what I'll be considering. And so when I consider the RT surface, so the union of all of these radiation CFTs, the two candidates are either these lower blue lines, which lies exactly on the horizon of each of these, or this upper blue line, which is the horizon of this big black hole. And okay, does that, I can say more, but does that answer your question for now?
Yeah, thanks.
Okay.
Oh, another question?
Yeah.
Can you prove that somehow like the arrow of time is going to the right in this picture? Like that
Good.
This process is favored?
So this requires, so to actually go from a state like this to a state like this to a state like this, we have to implement a Hamiltonian that sort of couples all these boundaries in a way that would not be like natural from the CFT point of view. So this is a Hamiltonian that we are defining to take us from here to here to here, etc. So that goes back to this con of unphysical dynamics. But the point isn't to have dynamics that look exactly like Hawking radiation. It's to construct a sequence of states that all look like they have, that it's an evaporating black hole that satisfies the island formula. Does that answer your question?
Okay, yeah.
Okay, thank you. So let me also mention that we're not just constructing these states willy-nilly. They're related to each other in a few important ways. So first of all, there's a constraint when we're doing this. So we have to we're deciding to conserve ADM energy. So there's some ADM mass associated to the original large black hole, and then when we imagine that it evaporates some smaller black holes, the ADM mass of the big guy goes down, and then those CFTs have an ADM energy that goes up. And we want the total sum to remain constant. So every time we take energy from the big guys and give it to when we take energy from the big guy and give it to the small guys, it's the same energy that we're taking and giving. 2, we're going to use the fact that in a 2 + 1 dimensional bulk, the entropy energy relationship between for black holes is that the entropy of the black hole is 2 pi times the square root of the central charge times the energy of the black hole divided by 3. Third, we're going to say for simplicity that each radiation black hole, so each of the black holes playing the role of radiation is going to be the same size little l. I said it was ADS size. You can pick a different size if you want, but for simplicity, let's just have them all be the same size L. Okay, and then going back to that question we got earlier, we can talk about the lengths of the candidate RT surfaces. So so bring back in this picture. Let's let this upper guy be called gamma prime. So this is the horizon. So this is the length of the horizon of the big black hole. And let's let the lower guys be gamma. So the union of all the horizons of the radiation, those will be called gamma. Okay, so the length of gamma is just we'll say n times L. So here I'm actually going against notation I said earlier. N is just the number of radiation CFTs that you have, the number of the radiation black holes you have. And so of course the length is just going to be the number of them times their total horizon length. What's less trivial is that the length of the big black hole's horizon, because you're conserving ADM energy and that this is the entropy energy relation, the length of this guy as a function of n is actually the square root of the square of his initial size minus n times L squared. So this is little l squared, square root of that whole quantity. So I thought if you sat down and you thought about these things, that you would agree with me that these are the lengths of both horizons as a function of n. Okay, and so now let's consider the entropy of the radiation as a function of n. So n is our proxy for time. And just to be clear about what I'm doing, I'm considering all of these CFTs, and I'm computing their entropy using the Ryu-Takayanagi formula. So when n is small, gamma is much smaller than gamma prime. And in fact, the entropy will grow sort of linearly. It'll grow linearly with n, because this is linear. Now, when now at some point, say here, these two are equal, and after that point, this one will be more minimal. And then the Ryu-Takayanagi formula tells you that now when we're now the minimal surface associated to that's homologous to all these radiation CFTs is in fact gamma prime. Okay. So at that point, you start using this length as a function of n, and it looks something like this. So this is, I claim, the page curve. Oops. Okay, the page curve in our model. Okay, and
a question at this level of discussion: is it essential that you deal with 1 + 1 dimensional systems, or can you just generalize straightforwardly to a higher number of dimensions?
You could generalize this, but we understand the states much better. Like I can construct the sequence of states for you. Like I can draw the geometries that you have to do the path integrals on in both the bulk and the boundary, explicitly in 1 + 1 dimensions, and not in higher dimensions. But the less, like qualitatively, I agree with you that it should go forward for higher.
Yeah, thanks.
Yeah. Okay. So that was the page curve. And I should also mention that one nice aspect of this was...
So sorry, one more question about what you said so far.
Yeah.
So from the point of view of the entanglement wedge, basically the point that you want to make is that the entanglement wedge for the radiation, so to speak, is gonna become the whole interior past the maximum in this curve, that in the page curve that you drew.
That's right. That's exactly right.
Okay.
That's exactly right. So let me say that now. So at this time, which you might call in subpage, let me get rid of all these extra guys. Okay. At this time, when gamma prime becomes the minimal surface, the entanglement wedge of all these radiation CFTs has grown to this. And so the entanglement wedge of all these radiation CFTs now includes the shared interior. And what this is supposed to remind you of is the fact that after the page time, in the other model, they computing the entropy of the radiation involved using some shared interior that popped up. Well, they didn't call it a shared interior. What they called it was this island that popped up. Here, you're supposed to understand that the shared interior is exactly analogous to the island. And so gamma prime and gamma are exactly analogous to the trivial and non-trivial islands. So that's such an important point. I'm going to come back to it in the context of quantum error correction now. So now let me turn to how this connects to quantum error correction, and therefore what you can learn about the island formula from our model in quantum error correction. Okay. So the connection between quantum error correction and islands. That's what we want to get at. And the impression that I hope to have conveyed so far is that islands are not this crazy new feature, but they're familiar entanglement wedge reconstruction. And we already know how entanglement wedge reconstruction is related to quantum error correction. So let me first discuss a little bit of, we sort of touched on this just now, but the connection to the island picture. So I want to make the analogy explicit between the model we just described and the models that the island formula is usually discussed in. Okay, so the model we just described looked something like this, where you had all of these radiation guys. So there were these, like, there was this set of horizons, and there was this horizon. This was gamma prime, and then the union of all of these was gamma. And we were always interested in computing the entropy of the radiation. So in the other picture, the typical island picture, we considered, so this was a late time picture for us, and for them a late time picture was something like this, where this is their region R, and there was some, when you computed the entropy, there was some region I that you had to include in this calculation. So my claim is that for us, R is like all of these CFTs. This is my claim. And then now let's remember the island formula. So the island formula said the entropy of R is related to the area of the boundary of I over 4G plus the entropy of the union of R and I. But R was supposed to be some different state. So what I claim is that it's actually less confusing if what you do is you don't write this as the same letter. You let's forget about capital R. Let's write actually a lowercase r. And what this lowercase r is supposed to denote is it's sort of it's like a bulk version of R. So let me make that precise by drawing the analogy here. So sort of inside, so the bulk picture up to, so look at say this part of R in this model. It has a bulk dual, and it itself has an entanglement wedge that ends on this blue surface here. I haven't left myself very much room to try this, but its entanglement wedge is part of little r. So it's the union of all of these entanglement wedges that are little r. Okay, is it clear what I mean? So capital R was like the CFTs, and then little r is the union of all of the individual entanglement wedges that end on gamma. So I'm claiming right now that that's the analogy. We can talk. So, but what that's supposed to do is make it clearer the relationship between R here and little r here. So I can say some more words about why. Huh?
A quick question. I mean, I think at least myself, I got a point in the change in the structure of the entanglement wedge in the style model. I think I did get it, but what's not clear to me is at what level this S of R union I enters, because I thought that like this would be so quantum field state.
Good. Yes. And
in these considerations that you did, like you have not really included this in the analysis, right?
Good. Thank you for bringing that up. Okay. So I claim that this is included in this picture, and the way it's included is as follows. So let me actually just blow up this picture really fast to this. So there's this blue surface, and then so is it clear what I've done here? I've just blown this up here. So this is like the boundary. It's part of this boundary, and I've claimed that the entanglement wedge all the way up to and including degrees of freedom right on this horizon is little r. Okay, so what's important here is that I've included degrees of freedom right on the horizon. So if you imagine that there are modes on this side of the horizon and modes on this side of the horizon that are entangled, which is what we believe for the vacuum, then when you compute just the entropy of little r, you get the entropy of these guys. So the entropy of just little r here includes the entropy of these near horizon modes. But whenever you include, so when you're in the late time phase where the entropy of capital R includes the shared interior, you actually have, so you have both sides of the horizon, so you have both partners and the entropy, and so you don't pick up this additional entropy from this guy because you also have his purification here. That is supposed to be exactly analogous to the fact that you had modes at late times here entangled with modes at late times here. That this term did not contribute much in this non-trivial I phase because you have both partners. Did that make it clear?
Well, I guess I did. Yeah, it's not, or it is. No, it's not. Unmuted now. Well, I'm not sure, but I think for the sake of the timing, maybe let's keep going and finish, and then maybe I will come back to this. Okay?
Okay, great. I'd be glad to talk about it. Okay, so it looks like I have 2 or 3 minutes left. Is that right?
Yep.
Great. Okay. So let me just really try and drive the point home about the connection between the island formula and quantum error correction. So quantum error correction gives us the following lesson, that we should think about the bulk as subalgebra of the boundary. So this was a lesson that was associated to this picture, where if I'd say divide the boundary, so this is again a time slice of ADS, and if I've divided the boundary here, and I could say divide it into some region R1, R2, and B. Here I'm being subjective. I mean, I'm trying to draw the relationship. Like R1 might be like half of these radiation guys, R2 the other half, and then B, this guy, the big black hole. And their entanglement wedges are each like this. And in this picture, we're all familiar with the fact that R1 has its own entanglement wedge, which I might call little r1. R2 has its own, which I might call little r2. B has its own, which I might call little b. And then they have this shared interior, which I might call little I. And we're supposed to remember that so this has the island formula in the sense that R1 union R2 has little I in it. But little I this is the important part. Little I is not a factor of the boundary Hilbert space. It is a factor of the code subspace. So the boundary Hilbert space does not admit a tensor factorization that includes little I as a tensor factor. Only the code subspace does. So any entanglement, for example, between R1 and I, while it looks from the bulk point of view like it increases the entropy of little r, does not contribute to the entropy of R1 union R2, for example. And I claim that it's through this picture that you should understand why in the island formula you have like one state here that's mixed and one state here that's pure. You should understand that's the relationship. It's quantum error correction. And that was the point I wanted to convey. Thank you.
Okay, thank you. We had quite a few questions already, but we can squeeze in a couple more if anyone wants to ask. Online.
Especially online.
Or if you want to come back to your topic.
Yeah. So if nobody has other questions, maybe we can come back to what you started explaining, because I thought that you're simply that, I mean, like, my understanding of Ryu-Takayanagi is that well, it's not really sensitive to this semi-classical corrections, right? Like coming from quantum fields in the bulk. So, for example, like the thing that you discussed here is about exchange of the saddles, right? It's similar to the analysis that you do for a black hole, or like two intervals in the vacuum in one plus one dimensional CFT, right? In which there's going to be different saddles, and you pick one length, right? So it's like it's completely analogous to this. And in this discussion, the notion of quantum fields in the bulk never appear unless you want to supplement your Ryu-Takayanagi into FLM, right? That you do. But so shall I think about what you're just saying in the language of FLM, or there's more to it?
That's a great question. So probably the cleanest answer would be to say yes, just include the FLM term, and then probably would be all more comfortable with it. But I do claim that just at the level of the area piece, you actually get something that looks like this. But when they wrote the island formula, it does not look very much like this with just area, because it explicitly includes this entropy piece. And this is what I understand you're getting at. So I claim that what this term is doing is captured by the fact that, well, let me say this, that in ADS CFT, the area term, it sort of depends on your RG scale, exactly what A/4G evaluates to. And that's partly because as you flow to higher and lower energies, it captures more or less of the entanglement across your divide. So like at higher energies, more of the entanglement across your divide is captured just by the FLM term, and less of it is captured by the area term. So that is to say that the area term is responsible for capturing the entanglement of modes just across the divide, and even though we don't always say it that way. And so it does capture the behavior of this guy in this model, is my claim.
No, I think now I see the point. I'm not sure yet if I agree, but at least I see what you wanted to say, so thanks.
Okay. Well, I'd be happy to try and make you agree.
No, this is good. I mean, I will look into the paper. I mean, like you're talking about
okay.
Paper. Yeah, I have like one more stupid question. It was about the Penrose diagram that you drew. I mean, now it's visible to the right side of your.
Oh yeah, this guy?
Yeah. So there is like this canonical association of time flow in this Penrose diagram, in a sense that like if you move in time upwards on the left hand side, or the right hand side, and downwards on the left hand side, this is the isometry of the eternal black hole.
Right.
And like if you move up like on both ends, like it's like this quench by Malacena and Hartmann. So, I mean, is there a reason why you thought about the flow of time on both sides this way, not the other?
Yeah. So I didn't want to do. So I think this was in their setup that I was taking it. So I think that they intentionally want both sides to be up so that you don't so that the state changes non-trivially.
Okay.
Yeah, because as you said, if this one moves down, then you would expect the state to remain the
So
same.
you say that like even if you couple this to the flat space, if you move down, like somehow like it's not this effect is not gonna come, or
That's right. So in the case where, so in the case I actually talked about with the coupling starting at t = 0,
yeah,
the situation's a little different from what I'm about to say. But in the eternal case where they're coupled for all time,
yeah,
it is, and then they prepare the Hartle-Hawking state of this coupled system.
yeah.
It is still the case that what you said is true, that if you move this side up and this side, left side down, that it's the same.
So somehow like you're saying that the Hartle-Hawking state is gonna have like ingoing radiation that makes the black hole not evaporate.
That's exactly right. So when they're coupled for all time, it's an eternal black hole still.
I see. Okay, thanks.
Yeah. Thank you.
Question.
Any last questions? Anyone online? Last chance. Okay. If not, then let's thank Chris again for this very clear talk.